Swayam Prabha. Digital India. Educated India.
Okay, anyway, I will continue, and people who don't show up on time suffer because of that. Okay, so this was the definition of the model, but let us just sort of make it clear. So I take a pile, even smaller because I am lazy. It is 4 by 3. This size is 4, this size is 3. So a configuration of the pile is any assignment of non-negative integers to these sides. Okay, so this can be 5, 2, 7, 1, 0, 0, 1, 0, 2, 0, 1. Okay, so this is the configuration of the sandpile. You can make another configuration, of course. Any configuration with non-negative integers is allowed. Okay, if height at any site is bigger than 1, this configuration is called unstable, because some site or the other in that configuration is unstable. Okay, so this one is unstable because there is a 5 here. So what will I do? So it says that if there is an unstable configuration, it relaxes to a more stable configuration by toppling. So this site is 5, this site will topple. So what will it do? The height will decrease by 2, it will become 3, and it will throw out 2 particles. One of these will go out of the system because there is only one side below it, right? And this one will increase by 1. So it has become this configuration. So the configuration C, which was unstable, under toppling will go to a configuration C prime. But C prime is also unstable just now, because it also has heights which are 3, right here. And this one is 2, which is also bad. So I topple again this one, this is 3, so let us topple here. So this will become 1, and this will become 4, and this one other particle will drop out of the system. New configuration, but it's still unstable. So I topple further. This 4 becomes 2, and this increases by 1, and this increases by 1. Okay, and then this 2 is also still unstable. So I make it 0, and this will become 3, and this will become 9. Okay, and this still is unstable. So it will become 0, and this will become 1, and this will become 2. Now, this is still unstable. So I keep on relaxing until everything is stable. Yes, sir. Whenever a site topples, it sends one particle to its downward neighbor, which is, if this is unstable, it will throw one particle here, one particle here. Yes, sir.
Sir, but in a site with 0 particles, sir, since it's empty space, won't another particle automatically fill that space?
Or there is nothing automatic. See, the grains themselves don't have any desire to do something. They topple, they just fall down wherever below, right? That's a more natural rule. And that is the model we are making. Our rule is that they fall down to 2 sides below. If the site is not there, it goes out of the system. Is there any question?
So, but if there is a free space, like in the between,
Huh?
in the middle of the thing, naturally the sand will come down, right?
Yeah, no. So in this model, there is nothing in between. These are the sites, and there are heights at sites. And under toppling, grains go from one side to another side. In between, I have forgotten or I have ignored. That is not part of the model. That's not part of my reduced description. I don't describe everything, I describe only some features of the problem. And in this case, I only have these many sites and every site has a height. You tell me this much, don't tell me what happens in the spaces in between. There is no such thing. Okay? Very good. So now, one of you will tell me.
Oh, we have a question over here.
Yeah. No, one site at a time. One toppling at a time. This will become something else under toppling, and this will become something else under toppling, and so on. I keep on toppling until it becomes stable. Once it becomes stable, then I cannot topple. Yes?
So two questions. When we're looking at toppling,
Huh.
do we look at all the possible topplings?
No, one toppling at a time, one side topples at a time. One toppling is one side topples.
And in that case, does the order of the toppling matter?
Very good. That's a second question. It says that if you have, this site is also here, this site is also here, then which one will topple first? That's a matter of the definition of the model. I can make the model, I say look from here and keep on watching till the first time it topples, then you topple that one.
So any one unstable configuration, based on which one topples first, it can lead to different stability.
Yeah, it could lead to different things. That is in general. So you can make other toppling rules, and one property which is true here, I don't know how to prove it, is that if you start with any configuration, whatever, eventually it will become a stable configuration in finite time. It cannot keep on toppling again and again. Okay? Yes?
There can be multiple stable arrangements.
Sorry, multiple stable?
Arrangements.
Of course, I said all the arrangements in which the sites are 0 or 1 are stable. So there are 2 to the power n stable configurations. Okay, the system will go to one of them. Which one? May depend on the order in which the topplings occur. It turns out that it doesn't depend. You can topple whichever way you want, and you will end up with the same final configuration. That's a very important, interesting property of this particular model we defined. If you make some other model, it will not be true. Okay, so in this model, there is a very important property, which is that it's called the abelian property. Okay, so it says 2 topplings commute. This is just a way of saying something. What do I mean by this? What I mean by this is the following. Suppose you have a big configuration in which there are all these sites, and this site and this site are both unstable. There may be other unstable sites, I don't care. But these 2 sites are unstable. Okay? Then what I can do is that first I can topple this, and then I can topple this, or I can do this in the reversed order. First I can topple this, and then I can topple this. Okay? Just one second. And the answer is that in both cases you get the same final configuration. If there are 2 sites which are unstable, you topple either this one first or that one first. After all, what happens? If this site is unstable, it will add 1 particle here, 1 particle here. This will add 1 particle here, 1 particle here. What is that final height at this site? It leaves 2 and adds 1. So its height changes by 1, decreases by 1. And this will be the same whichever order I do this in. Right? So the proof that these 2 topplings commute just reduces to the proof that in integers you can first subtract 2 and then add 1, or first add 1 and then subtract 2, you get the same answer. Yes, sir.
So if it takes n configurations from C unstable to C stable, then n topples are occurred.
I don't know. Okay, so for example, here I had said that this height is, let us say, 9. What will happen if this height is 9 and I relax here? It will become 7. And the two particles will leave the system. But 7 is also unstable. It will become 5, then it will become 3, then it will become 1. Once it becomes 1, then it's stable.
Yes, sir, but since you're assuming that each topple occurs separately,
Hmm.
so in one configuration, only one topple occurs.
Yeah, no, so very good. So topplings occur. Okay? Now the statement is that two topplings, which order they occur, that doesn't matter. So now I will go above and I'll say, okay, you topple whichever way you want. You just tell me what is the final configuration. I don't care about the in-between ones. And then everybody will get to the same answer.
Then how do we reach the other stable states?
So you add somewhere, this is one stable state you reached. But now you add one more particle, then you go to another stable state. Then you add one more particle, you go to another stable state. And so on.
From one unstable state, without doing anything, you can only get to one stable state.
Yeah, unique stable configuration. Okay, every unstable configuration leads to a unique stable configuration, independent of the order of topplings. That is the result. And as I said, the proof is actually some high school or even 5th grade arithmetic you have already learnt. So nothing very deep about this one. The point is that this result is not true for arbitrary models. It's only true for this model. If I had some other rule which said that, two particles can go here and this one can lead to particles going there or some such thing, then maybe this result is no longer true. You can ask for what class of models is this kind of result true, and it turns out that it's not true for everything. It's only true for some models, not everything. Okay? All right, very good. So, two topplings commute, and the next result is that if you start with a stable configuration, C. Stable configuration is being denoted here by C. Add at some site called I, you go to C prime. Then you add at J, some other site J, and you go to C double prime. Some other stable configuration. You add and you topple as often as needed until you get to a stable configuration. And we are only looking at the stable configuration. You add a particle and go to a stable configuration, then add one more particle, you go to a stable configuration. Just 1 second. Now I will do the different. First I will add at J, then you will go to some other configuration. Okay? And now I add at I. What configuration will I go to? The answer is it's the same. Still go to C double prime. There is a unique configuration which is obtained after I add and topple everything. It is a surprise. It is not immediately obvious that that should happen. Okay? And I leave the proof to you. Because it involves only 5th grade mathematics, I think you should be able to construct the proof yourself. Okay? It's actually not 5th grade mathematics, I'm making a joke. But the proof is not so hard in the end. And I'm sort of challenging you to produce the proof yourself. Okay? But now let us develop some, it's called formalism or notation. Because it is useful. So these results.
Sorry, we have a question.
Yes. Yeah.
So if one site is having 3 particles,
Yeah.
then the site can either lose 2 particles or it
No, the rule we gave was that it loses only 2 particles. J goes to J minus 2, that is what was written. Yeah, there are other models people have studied in which it loses 3 particles, and then this abelian property is not true. Then the results are not independent of the order in which you do the toppling and all kinds of stuff. Okay, so this model happens to be simple, but it has some nice properties, and that is why it is more interesting than the other variants in which you can change the rules, but all these nice properties don't remain true anymore. Yes.
So even after adding another J and another I to still go to C double plane.
Yeah. No. So I start with C. Same starting configuration. And I first added J, first added I and then at J, I go to something. Or first add at J and then at I and go to something. You get the same final configuration, that is the result. Okay? Is that clear? Yes.
Is it compulsory for a site to lose the same number of particles on either side?
Yeah. That is by definition of the model. The model said J goes to J minus 2. There is no choice.
Also, the proof that you're asking us to derive, can you repeat what exactly is this proof?
The proof. No, I didn't give the proof. I said the proof involves 5th grade.
She wants the statement.
The statement is precisely this. Okay, start with a stable configuration. Configuration C. If add at site I, then at J goes to C prime. Okay. If first add at J, then at I, still goes to C prime, goes to the same answer, goes to same final state. Okay, and this is true for all I, J, C. Whatever initial configuration you pick, whatever site I you pick, whatever site J you pick, it will still be true. There are 2 to the power n possible stable configurations. It's true for all of them. And the proof is the same, it's not a big deal. As I said, that if you start here, and okay, so let us give you an indication of the proof. I have this big configuration. I have these 2 sites. Suppose these 2 sites are different. Then if you add here, if it doesn't topple, or if you add here, it doesn't topple, then you add here, then whatever happens, happens. Right? So it is easy to convince yourself in simple examples. Take one stable configuration and see that it's true, take another one, it's true. But constructing a proof that it is true for all possible choices of stable configurations is trivial, non-trivial, but not difficult. So we are not doing that here now because I have a limited amount of time. But let us discuss some formalism. Formalism is just a notation to help us in future or some such thing. So define addition operator A sub I. Okay, it's an operator. What does it mean? It means that A sub I on C is equal to C prime. By definition, AI acting on a stable configuration says you add a particle at site I, relax as much as you want, as needed, and the final configuration is C prime. The operator is like a slot machine. This is the operator. You add a configuration C and it outputs a configuration C prime. C is stable, the C prime is stable, and what it does in between is to add the cited I, topple everything and get the final answer. I don't want to get into the details of how it does the toppling inside. Okay? And then I can define AI, AJ of C. So here it says that, you know, this is configuration C, AJ of C is also a configuration, stable configuration. So I start with C, apply the operator AJ, you get another configuration, apply the operator AI, you get another configuration. Just 1 minute. And you get a result which is the same as if you did it in the other order. Yes, sir.
So AI means adding other I inside.
And relaxing until you get the stable configuration. Yes. Sorry? No, CIS. It says that if you start with any stable configuration C, first add at J, then at I, and get the final stable configuration, then you will get the same result if you first add at I and then at J. Whatever we said in words, now you can write some small equation for it. Okay? It doesn't add more, but sometimes this formalism is useful and it is powerful. Power comes because saying since it is true for all C, I can just write AI AJ is equal to AJ AI. Now it is an operator equation. Just 1 minute. So if you take operators, you can multiply them. In the sense, you can first operate with one and then with the other. And this one says that the multiplication of these operators is commutative. Yes.
So you told that C prime will be stable here, right, sir?
Sorry?
AI of C is equal to C prime. C prime stable.
Yeah, by definition. AI acting on something gives you another stable configuration, nothing in between.
So, but if C has if C is having two sides which are unstable,
Yeah.
and then AI will give you another configuration which has one unstable.
No. AI applied on a configuration, you have to relax again and again until you get a stable configuration and output the stable configuration. Yes. Anything else? Okay, very good. So let us, just for practice, I'm very lazy, so I take only this 5-site configuration C equal to this configuration. Let us make 1 0 1 0 0. Okay, and now because everything should be, so I will call the labels will be denoted by something else, not letter, not numbers. It confuses to have too many different. So if I act A alpha on C, means add one particle at site alpha. What will I get? Final stable configuration. Can one of you come to the board and work it out? One of you? Is the question clear? The question is, this is my sandpile, 5 sites. This is the configuration C, 1 here, 0 here, 1, 0, 0. It's a stable configuration. I add one particle at site alpha. That is, apply A alpha on this configuration. What is the resultant final configuration? That is the question.
So AI means you'll get a configuration where ith side is stable or the entire side.
No, the full configuration has to be stabilized.
So then AJ of AI of C will be useless, right? Because you're applying AJ on a stable configuration.
Yeah.
So then that does nothing, right?
That nothing means what? It is another stable configuration. Okay, very good. Explain to everybody what you are doing.
So we're adding one particle to alpha.
Yeah,
So when we add one particle to alpha, it changes from 1 to 2.
Yeah.
Then it will topple. So when it topples from 2, it becomes 0, and 1 will exit the system, and this will become 2.
hmm.
And then this will topple again, 6
Hmm.
and 7, so this will become 0, and these two will become 1.
Very good. So that is correct. So this is the final configuration C prime. Is this clear to everybody? It's a very simple mechanical process of obtaining the final configuration based on just simple toppling rules. If the C was a much bigger configuration, doesn't matter, you just mechanically keep on toppling until it reaches a stable configuration, and that is the answer. And now this statement seems more interesting because it's true for whatever size of sandpile you make and whatever site I and j are. I and j can be the same site also, that's not a problem. Then the equation is trivial, a squared equal to a squared, that is, doesn't require any proof. Okay, very good. So we have done this much. Okay. So now I want to calculate exactly the steady state we want. So we want to know what is the steady state of my model. Okay, so I take some pile, I keep on adding at random, at arbitrary site. I pick a site at random, I add there, topple until it relaxes, then see what's the configuration, then add at another site and keep on, then relax it again, then add at another site, relax it again, and so on. After you have added many sites, it becomes in a steady state. And then what happens in the steady state? In this simple model. So this is my model. But this configuration is not known now. It's anything. Any of the possible 32 configurations is there, they all occur with some probability. Okay? So I want to know what is the steady state of this system. Okay? And now let us try to think about this. And so what I realize is that suppose I look at the top layer. What happens here doesn't depend on what happens below. It's not affected by things whether they topple, don't topple, it's 1 or 0, I don't care. Okay? So if I only want to look at what happens to the top layer in the steady state, forget about this stuff below, is the same answer as far as the top layer is concerned. You can take the full model or take the top layer only, and it is the same answer. For the top layer, the answer is very simple. If this might be 0 or 1, when you add something to 1, it becomes 0. When you add something to 0, it becomes 1. That is all that happens. And it doesn't affect other sites on the same row. Okay? So when I keep on adding at random, zeros will become 1, 1 will become 0, and so on. And at long times, all allowed configurations of 0 and 1 are equally likely. Is that clear? Okay. So what are the allowed configurations? In this case, there are only 4. It could be 0, 0, 0, 1, 1, 0, or 1, 1. And all these are equally likely. Each occurs with probability 1 by 4. Okay. But maybe I didn't have just these, I had these 4 sites in the top row. Doesn't matter, the same answer works, and all the possible configurations of 0 and 1 are equally likely. Right? I don't have to work harder, the same argument works again. Okay, so So now I take my L by M lattice and I look at the top layer and I ask that what is the probability that if I add a particle, no toppling will occur. I add a particle at a randomly chosen site, no toppling will occur. Can anybody of you give the answer? Yeah. So the answer is that nothing will occur if the site is 0. If the site is 1, then the toppling will occur. What is the probability that the site will be having height 0? It's half. So the probability no toppling on adding a particle is equal to 1 by 2 on the top layer. Okay. So now let me simplify the problem further. I will only add at the top layer. I have this big lattice, but I will only add particle somewhere on the top layer. I will not add below. Okay. And then this argument is working and I know what the probability that no toppling will occur. But now I want to ask a slightly more complicated question. I want to ask what is the probability that exactly one toppling will occur? Number of topplings equal to 1. What is this? This is more complicated because I add here, there is a 1 here. If it is 0, then this will not topple, so it doesn't matter. If it is 1, then it will topple. But we are saying, okay, probability of toppling bigger than or equal to 1, that answer is half. That is easy. Because that will topple and after that some other topplings will occur or not occur, I don't care. But if I want to say what is the probability that exactly one toppling occurs, means that below it both sides must be 0. Because then this will go and fall down there and they will not topple. Yes? No.
So like possibility of 0 is 1 by 2. So
Hmm.
there are 2 places. So 1 by 2, 1 by 2 is 1 by 4.
So, no, let us go slowly. I think I need to know what is the probability that in the next layer there will be 2 zeros. It's yeah. 1 by 8 is the correct answer. But we need to be careful and we need to realize that what I am now doing, I am calculating what is the probability of things happening in the second layer. On the top layer, things were simple because everything was independent. In the second layer, they are not independent. When I add something here, 2 things add at the same place and adjacent sides. Okay, so the problem is slightly complicated. But let us not go into it now because my time is limited. You can actually show, without too much trouble again, that in the second layer also, all allowed configurations are equally likely. Okay, and so even in the second layer, each site is independently 0 or 1 with probability half. Yes.
So, but doesn't it depend on the number of particles on the top layer?
No, it doesn't depend.
So like for example, if there are n particles on the top layer, from those n particles you have to choose one particle, make sure it has one sand and every other particle. So all n minus 1 particles should have 0.
No, very good. No. So let us be clear. So my statement was that I go to the steady state. No. It's a good question. Let me answer. The point is, the statement is, let me go to the steady state. I don't know what is the top layer. Then I just add a particle and say what is the probability of toppling. Okay. If I know the configuration of the top layer, the answer is fixed. But I don't know the configuration of the top layer, then I have to average over all possible choices and then the answer is half. Okay, I'm not allowed to, right now I'm not saying that I know what is the top layer. I'm averaging over all possible configurations of top layer or all possible configuration of the pile. And the statement which I will not prove here now is that all stable configurations are equally likely. Okay, this statement I should prove. But if I prove this, then it will take the rest of the time, and it will perhaps you will feel bored and sleepy, and maybe I should not do this here now. The proof is not tough, but it's just a little bit of careful analysis, and I leave it as an exercise just now. Okay, so very good. So you can show that in this model, in this particular model, I don't care about other models, all allowed configurations are equally likely. All allowed stable configurations are equally likely in the steady state. If there are n sites, there are 2 to the power n configurations, and all of them are equally likely. Okay, so now I am actually able to do this. So probability that S equal to 1, S is the number of topplings when I add a particle at random on the top layer, and this is equal to 1 by 8, because in order for this to have only one toppling, this side should be 1 and both of these below should be 0, so that when it topples here, no further topplings occur. This occurs with probability half, this occurs with probability half, this occurs with probability half independently, so the full answer is 1 by 8. So I have calculated the probability that the number of topplings is exactly 1 is 1 by 8. Not a lot of hard work. So now, since I have done this, I am sort of encouraged to try this one. What's the probability that exactly 2 topplings will occur before it reaches a steady state? It's stable configuration. Okay? And the answer is that, well, you could start with something, it will have to topple, and then it will throw out 2 things, and then one of these should topple and the other one should not topple. Okay? So this should be 1, and this should be 1, and this should be 0. You calculate the probability of, and this should topple and stop. So below this should be 0, 0. Okay? Or I could have the other case where this is 1 and this is 0 and this is 1 and this is 0. This configuration. These are the only cases where S equal to 2 can occur. Yeah? S equal to 2 means 2 topplings. I add here, then this will topple, then this will send one particle. This will not topple because it's a 0. This will topple, but these are 0, so there is no further toppling. Exactly 2 topplings occur. And the other case is that one is on this side, doesn't matter. Okay? Yeah, so 1 by 2 to the power 5. There are 1, 2, 3, 4, 5. 5 sides. This thing occurs with probability 1 by 32. This thing occurs with probability 1 by 32. And so the full answer is 1 by 16. You add those 2 configurations. Okay? And now I'm not going to do this, but it is clear. If I want to work out what is probability of S equal to 3, all you have to do is you have to say how can 3 occur. 3 can occur in, maybe this one has a 1 here and 0 here and 0, 0. That's a possible way 3 can occur. Or maybe it is 1 here and 0 here and 0, 0 here. And something, maybe this one is, this is 0, this is 1, and so on and so forth. All allowed configurations will give you a S equal to 3, can be listed, enumerated by hand, exhaustively, you don't miss out anything. Each one has a probability which you can work out, and you add up and give you the answer. It's a little bit of work. It takes me some few minutes to get the correct answer right for s equal to 3. And it takes me much more time to get s equal to 10. But if I want to do s equal to 10, maybe I write a computer program which will enumerate all possibilities and add them up and give me the answer. Okay, so this can be done, and one can work it out. And it turns out that, so I can then plot probability of S versus S, and it gives you a graph like this. There is a maximum possible value of S, which is the maximum number of topplings which can occur in a given problem. So if you have a pile of height m, then maybe everything topples. Everything topples at most, every side topples at most once in this problem. You can try to prove that. And so I know what is the maximum possible number. If I say that for this pile, what is the probability that 1 million topplings occur, the answer is 0. So there is an S max. But interestingly, what happens is that if you take S equal to 2 or 3, it doesn't depend on L and M, so long as they are big enough. See, we were working with finite configurations. If L is bigger, it doesn't matter whether it is. The value of L by M lattice, values of L and M don't matter in this calculation so long as L and M are big enough. It's a great reduction in the problem because normally the answer depends on L and M. You have a steady states depend on what's the size of the system. In this particular case, it is turning out that the answer is not dependent on these details because it's a very simple model. Okay, so that is the advantage of working in this model. So what people do is they calculate probability of S in a system of size Lm, and they take the limit L goes to infinity, M goes to infinity, and let's call that probability of infinity S. So the size of the system is now no longer important, okay? And then this graph looks like this, and this function has a power law tail, okay? So this prob S goes like 1 upon S to the power 4 by 3 for S going to infinity. This wiggle mark means that actually there is a constant in front which I didn't write down. It has a power law, the power is 4 by 3. There is a coefficient which exists, it's fixed and finite, but I didn't write it down just now. I can work it out. It turns out that the full solution for this prob S can be worked out, but that requires more work. And the answer is some airy function if you are fond of such functions. So it is complicated. It is not going to be as trivial as all the discussion so far. It will require some more work, but it can be done. It is not a major problem. Okay? It's an algebraic detail which I am ignoring just now. I am saying that prob S can be worked out in this model for arbitrary S equal to 15. I said you can write a computer program. If you have a patience, you can work it out with pencil and paper. It's not a problem. There is no conceptual issue involved. It's just that how to work it out. Can you work it out more simply than writing a complicated program? Turns out that you can work it out, but I'm not doing it here now because I'm lazy. Okay? So what do I want to do instead in the next 6 minutes? Let me see. I keep my notes so that I don't forget to do something. So I can do this, but I can also discuss something else. There is something called the duration of the avalanche. You imagine that you add a particle, then all the sites which are unstable you topple in the next time step. And then some sites more than one may become unstable, you topple them in the next time step. And you topple them in the next time step until everything becomes stable. So how many time steps you need is called the duration of the avalanche. Okay? So of course if S is 0, no toppling occurs, then the duration is also 0. If S is 1, the duration is 1. If S is 2, the duration is 2. If S is 3, the duration can be 3 or 2, I suppose. You know, because 3 sides could topple like this. Then the duration is 2. But if they topple like this, then the duration is 3. But it turns out in this case that suppose both of these sides topple. This is 1, this is 1, this is 1. Then this will, you add something, it will topple here. These two sides topple, each of them sends out a particle. Even if this one is 0, it will topple. Okay? So S equal to 3, this cannot be S equal to 3, this will have to be S equal to 4 or more. So in fact it turns out that if S is 3, the duration is 3. But this doesn't continue, and you can certainly have a case where S is equal to 30, but T is only 15 or some such thing. Okay? So the duration can be worked out, and the probability, the duration of the avalanche is greater than T, can be worked out by the same method. We have already worked out the method. You just start with something and say, okay, it has to stop by time T, so only these configurations are allowed. Give a list of them, add them up, and that gives you the answer for each finite T. And then I just take T equal to 20 and until my patience runs out. And then this can also be shown to be a power law. It goes as 1 upon T to the power half for large T. Okay, so what are these exact functions? That requires some work which we are not doing now. Okay, but it can be done. And what we would like to do instead is to actually show that whatever the answer is, it's going to be a power law. Okay, can I show this much more elementary result? I don't know what is the power, it is 4/3 of √2 or whatever it is. But is it a power law or is it exponentially decaying with S or some such things, decaying as exponential square root S or some such funny function? And that result is actually easy, and that is what I want to do here. So, proof that probability of S is a slowly decaying function. So slowly decaying function means it's a power law. Okay? So can we prove this from direct, simple arguments? And the argument is like this, that I have my sandpile, I add a particle, it goes and sits there, and then it, after some time it will topple again. Maybe it doesn't topple right now, but eventually it will topple again, it will go down further, and it will leave the system. And then I added another particle, and that will also leave the system, and third particle will leave the system. So I add 10 to the power 6 particles, one after another, and most of them eventually leave the system. Some particles are still inside here. Okay? So I can define what is called the mean residence time of a particle. Okay? So suppose there is a particle, it topples once, then its height decreases by 1. And then it will topple again and its height will decrease by 1. Sometime or the other it will topple again, its height decreases by 1. In the end, when the height decreases by m, then it leaves the system. So if I look at the path followed by one grain, it will say this particle started here, then it moved to the, I don't know which way it moves, so it may move to the left or right, but then it moves like this and like this and like this, and eventually it leaves the system. For each grain, I will mark it and I will calculate its trajectory and look at the average properties of this trajectory. And the first claim is that all the trajectories have length equal to m. Okay? So each particle will go down m times, right, till it leaves the system. And so mean residence time is a complicated stuff. I changed my mind. Mean number of steps. Okay? This is an exact result and it is easy to see. Is this point clear? Yes. Sorry? Very good. No, so usually I consider cylindrical boundary conditions where things are periodic in this direction and they can only leave at the bottom, they cannot leave from the sides. Okay? If you want to leave from the side, you can modify this argument appropriately. Okay? So, mean number of topplings per added particle is equal to m. In fact, the number is always m. If I mark a particle and until it leaves, it will go exactly m topplings. Nothing it can do. Okay? So I will take this system and I will add particle and I will calculate S1. S1 is the number of topplings which happen when I add the first particle. S2 is the number of topplings which happen when I add the second particle. S3. And I keep on adding until I get all these 10 to the power 6 particles. Then I add all these numbers. This is the total number of topplings which occur when I add 10 to the power 6 particles. And the answer will be 10 to the power 6 times m, more or less. Because each particle takes m steps and most of them have left, so it's 10 to the power 6 m. So, summation Si is equal to up to time t is t times m, give or take a little bit. These error terms can be controlled, but we are not getting into that just now. And so, what it says is that what is the expected value of S1? So if I take, so this implies that if I average over all I, summation Si divided by number of things, that is the average of S. And so the statement is that average of S equal to m. It's an exact equation, it is not an approximate equation. with the definition of average as defined in the steady state and m going to m large or whatever. Okay, just 1 minute. And so, now if I let m go to infinity, then the average value of S becomes infinite, or average value of S increases as m increases to infinity. So then if I define probe S times S summation over S, that is the expectation value of S. That is the definition. But this is infinite. This is probe infinity. Okay, and so this means that the distribution must be such that the first moment diverges. And so probe S must be power law. If it is an exponential, the first moment will not diverge. Sorry? Yeah, so the statement is that the expectation value of S is equal to the number of steps the particle takes to reach the bottom, but this number will diverge if m diverges. So in the limit of large m, the expectation value of S must diverge, which means that this function should be such that it has a power law tail. It must decay slower than 1 by S squared, otherwise it will not diverge. Huh? Then the first moment will not be infinite, it will be finite. First moment of the distribution. Expectation value of S. If S is decreasing as exponential, then its first moment is finite, whatever it is. Okay? It can diverge only if it is a power law. So this is a very general proof. In fact, all the details of the model we didn't use. We only use the fact that it has to take an infinitely, it has to take a very large number of topplings to reach the boundary. And that is enough to prove this result. And says all these kinds of Sandpile models will have power law tails in the distribution functions. So then I will stop here now.
Thank you, sir, for your insightful lecture. Your explanation of the Sandpile model was really simple and really easy to understand. From telling us how we use heavy approximation in such complex models to stable states, how they are achieved, I'm sure your lecture helped us relate higher order problems to simpler ones. Thank you once again for your time and expertise.